So, hi everyone. Hello. Welcome to this new episode of our climate seminar series dedicated to climate change adaptation and mitigation. My name is Charmy Lino. I'm project manager at Climate. I'm going to introduce you at this seminar. It's a special edition today because we co-organize it with the Expertise Center for Climate Extremes, also called ECCE as its acronym. It's a very new center that has been inaugurated a month ago and is dedicated to research, both research and the contact with the more general public and society. Another reason why it's a special edition, it's a hybrid format. So we have our usual Zoom. Hello, everyone who watch us on Zoom now. And here in person, thank you for joining us at the Geopolis building. First, we're going to have an introduction, as you can see, a presentation from Manuela Brunner and then Tom Beucler. Both presentations will be in English. Don't hesitate if you have questions in French. We can either translate them for our speakers or our speakers can also answer in French. Also, if you have questions, we're going to pass on the microphone in the audience, and people online can, as usual, raise their digital hand. So without further ado, I will leave Tom Beucler introducing Manuela Brunner. Thank you.
Hello, everyone. So I'm Tom Beucler. On behalf of ECCE and Climate, it's my absolute pleasure to welcome Professor Manuela Brunner here at the University of Lausanne. So after a master in climate science, followed by a PhD in hydrology at the University of Zurich and the Université de Grenoble, Manuela went on to a postdoc in the US, if I'm not mistaken. And then we're very glad now she's back in Switzerland and she's an assistant professor. She's joined between the Institute in Atmosphere and Climate at ETH, Zurich, and between the Swiss Institute for Forest, Snow and Landscape Research, also called the WSL. And she specializes on in the impact of climate change on water extremes in the broadest sense. And so with a special focus on extreme events such as floods and droughts. And I'll hand it over to Manuela. Thank you so much for joining us today.
Thank you very much, Tom, for this very kind introduction. Is the sound okay for everyone? Great. And thank you also, Climate and ECCE, for having me over. It's a big pleasure to have so many exchanges with you today and also to show you a bit what we're doing in Davos and at ETH on climate and water extremes. Today, I'll give a very general talk about climate and reservoir influences on droughts, floods, and also their transitions. And I hope that's something for everyone. We're going to start with a picture from the flood event 2021, which you probably still all remember as a very impactful event that led to huge infrastructure damage, to large costs in the infrastructure sector in Germany 2 years ago. And this is just one example of showing that floods, they are indeed very destructive and impactful. On the other side of the coin, or the extreme event spectrum, we have the droughts, and this is a picture from 2018, an event which you also still remember. It led to very low water levels. It had severe impacts on fish, on energy production, and also the agricultural sector. And just illustrating that also the other type of extreme can be very, very impactful. In our research, we study both types of extremes, both floods and droughts, and also how the two types of extremes interact. Both of these types of extremes, they can of course be studied as natural phenomena in very natural upstream catchments, but in reality, these types of extremes, they're influenced by humans, and they're influenced in two main ways. One way is climate, and we all know that through our carbon emissions, we influence climate, which is why I would also call that a human influence. And I would today like to show you how climate change affects both floods and droughts and also their transition. Then, very importantly, these extreme events, they're not just shaped by our indirect influence on climate, but they're also very directly shaped by direct water management, water abstractions, water regulations, or also water diversions. And I would, in this talk, like to discuss both types of influences, the influence climate change has on extremes, but also the influence our direct regulation effects have on extremes. Before I jump right in, I have to define what do I mean by droughts and floods. When I talk about droughts here, I mean stream flow anomalies, which are defined as times when our stream flow curve in black falls below some threshold, here in gray, and we're talking about seasonal flow anomalies rather than absolute deficits. In terms of the floods, instead, we're setting a fixed threshold. That means we're looking at absolute peaks or high flows, which we can describe not just by the peak, but also by the volume and duration of an event. And I've already mentioned that we're also interested in the interaction between the two types of extremes. And here we're mostly interested in rapid and seasonal transitions. The reason for this being that a flood happening shortly after a drought might have very impactful results, in the sense that these flood events are maybe a bit less expected than floods happening in a wet period and might lead to additional management challenges. And here we simply define transitions as events that happen very close in time to each other, and we're also using the term transition time to describe the time elapsing between the end of a drought and the start of a flood. Now let's first look at the influences of climate on drought events. And what I'm here showing you is a picture of the European Alps. You see Switzerland here in the middle. And we've looked into the main driving processes behind drought events over the Alps. And what we find is, depending on where we actually are, there's different driving processes, anything from rainfall deficits, snowmelt deficits, or also groundwater deficits that can lead to these drought events. In future, the processes that are leading to these drought events, they're actually changing. And this is what I'm showing you on these two maps. On the left, we see changes in the importance of rainfall deficits leading to stream flow deficits. And as you see, purely rainfall deficit-driven stream flow deficits or droughts, they become less important, suggesting that it's more and more important how different deficits or how different processes actually interact with each other and lead to stream flow deficits. A bit different here on the right, here I'm showing you how snowmelt deficits as an influencing factors change importance over time, and blue means that this process over the Alps becomes more important as a driver of stream flow deficits. So that means in future, and also right now, we already see that drought events that occur in the Alps are more and more often driven by snowmelt deficits, which are very closely related to the changes in temperature in winter. And that's something we observe today, and we expect to observe even more of in the future as temperatures continue to increase even more. These changes in drought generation processes, they have direct effects on both the seasonality of drought and also the magnitude of drought. Here, I'm showing you the seasonality distribution of stream flow deficits happening over a historic period from 1970 to 1993. And we're in colors looking at the months of occurrence of the drought. That's labeled on the y-axis. And on the x-axis, you see the catchments kind of aligned from very low elevation catchments on the left to very high elevation catchments on the right. And what this figure tells you is that at low elevations, stream flow droughts, they happen mostly in summer. And the further up you go, the more likely it is that these droughts also happen in the spring and winter and in other seasons outside of the summer season. If you now do the same thing and look at how these seasonalities have changed until more recently, we see that 1994 to 2017 actually shows quite a different picture. Colors have become more orange, also at high elevations. And this means that drought occurrence has shifted in high elevations more towards summer versus winter, also highlighting that these snowmelt deficits actually have become more important and lead to more frequent drought occurrence during the summer month. And again, this is something we already see in the data, and we expect this seasonality shift to be even more pronounced as we move into the future. Related to this seasonality shift, we see changes in drought intensity and drought magnitude. Here we're looking at trends over the period 1970 to 2017. And we're looking at the three characteristics: intensity, that's the minimum flow; drought deficit, which is kind of the deficit volume; and also the drought duration. In terms of minimum flow, there's actually some good news, because minimum flow is mostly increasing. That's what is illustrated here by the blue colors. When we look at deficit, we actually see that deficit is increasing over the alpine range. That's maybe a bit more bad news. And again, that's related to the fact that we have less input from snowmelt. And last, we see a decrease in drought duration in the Alps, which is probably a good thing, but droughts tend to become longer in the low elevation catchments further down in the lower elevations of southern Germany and also northern Switzerland. So in summary, climate change already has a visible effect on drought characteristics, both in terms of duration, deficit, and minimum flow, which is a result of changes in seasonality and changes in drought generation processes, from rainfall-driven deficit droughts to more snow melt-driven droughts. Now we've seen droughts are clearly changing. There's evidence for that. What about the floods? Are they changing too? And similarly to the droughts, floods are driven by different types of processes, including essentially the opposite processes as before: an excess in precipitation, very large snowmelt contributions, and also saturated soils, which can be super important. As floods have a slightly lower signal to noise ratio, we cannot just look at observations, because we see not very strong trends, and we don't essentially see how floods are changed or have changed over the past decades. And this is why I'm here using a model to look into the changing processes that generate floods in future. And I'm here always showing you some maps which have been produced by different climate model chains, each consisting of a global climate model, which is coupled with a regional climate model. And then we're feeding that through a hydrological model to generate stream flow simulation. Each of these maps shows you in blue colors regions that show a positive trend in any given variable, and in red catchments that show a decrease in any given variable. As you can see, when we look at precipitation, which is one of the main drivers of flooding, we see that many regions in Switzerland, especially in some model chains, show a clear increase in extreme precipitation into the future towards the end of the century. Similarly, we see quite clear changes in the snowmelt contributions to flooding. These decrease, which has potentially an alleviating effect on floods. But at the same time, there seem to be some increases in soil moisture, especially in winter, which again has a negative effect on flood risk. And as you might imagine, all these different processes, they actually play together, which makes it quite difficult to predict flood peaks into the future. And this is what I'm showing you here. This is simulations for changes in flood peaks and flood volume. And you see many white spots on the map indicating that the models actually don't necessarily agree on the question of whether or not flood peaks are becoming bigger or smaller in future. And that's really a problem of of noise and signal. These floods, they have a very large internal variability, which makes it very difficult for us to separate a clear change signal from this large internal variability. And the question is, given that we do know that precipitation, especially in summer and especially the very intense precipitation events are increasing, why don't we see this reflected in our streamflow projections? Why aren't there more blue dots on this map also showing that floods are increasing? Answering this question of how precipitation, extreme precipitation translates to floods is not so trivial, as I've said, because of this large noise to signal ratio. And therefore, we need different tools than the tools I've used before. We need some large ensemble that allows us really to describe the internal variability and to separate it from the signal. To do that, we're using a tool that is called Single Model Initialized Large Ensembles, in short, SMILE. And these SMILEs, they're a bit different from the usual models chains you might be used to, in the sense that they only rely on one single global climate model, which is fed by or driven by one single greenhouse gas emission scenario. But at the same time, this model is run with many different initial conditions, in our case, 50 different initial conditions, which will allow us to quantify internal variability. Since we're interested in flood changes in the Alps, we need some statistical downscaling to get from the very coarse resolution of the global climate model to regional climate models. We then feed these simulations into a hydrological model and get a large ensemble of climate simulations that allows us to look into future changes in flooding. And now to study this relationship between changes in precipitation and streamflow extremes, we extract precipitation extremes, identify the corresponding streamflow extremes. For each of these variables, we do a frequency analysis and determine quantiles corresponding to different return periods, from moderately extreme events of 10 to 20-year return periods to very extreme events with 100 or 200-year return period. And then we'd simply compare these quantiles in a future period from that 2060 to 2099 with a historic period from 1961 to 2000. If we do that, this figure now shows relative change versus different return periods. We clearly see that independent of the return period, we have a clear increase in precipitation or in the frequency of extreme precipitation, with this increase being stronger independent of the severity of the event. So the more severe the event, the stronger is the increase in its frequency. If we now turn our attention to this chart, this increase with return period is still visible, but we see that for the moderately extreme events, there's actually no increase in flooding. Instead, there's a decrease or hardly any change depending on the catchment where you are, which is because of the moderating effects of soil and snowmelt influences, less snowmelt contributions, drier soils, and there's just not such a direct translation between the increase in precipitation and streamflow. But then when you move to the very extreme precipitation events, you see that independent of the soil conditions, independent of the snow contributions, these extreme precipitation events will translate to increases in flooding. And we've found this threshold above which increases in precipitation are actually reflected in increases in flooding, and below which precipitation increases are moderated by land surface processes. So all in all, we can say, yes, at some point, if we're really looking at the very extreme floods, we do see that these are increasing, but for the not so extreme floods, the picture is not very clear, and the interplay between different processes makes it difficult to make any clear prediction on the change of these processes. Now, what about the transitions? Because we've now talked about each of these individual extremes separately. We've seen that both types of extremes are changing, and this suggests that also the interplay between the different processes might be changing. I'm here showing you a map which was produced by one of my PhD students, Jonas Goethe, who has determined drought-to-flood transitions over the United States. And for each of these transition events, he's looked at the seasonality of occurrence. Blue colors indicate that transitions are happening more in the winter period. Orange, red colors suggest that transitions are more happening in the summer and fall period. What he shows is that over the United States, over different hydroclimate, these transition timings vary a lot, with transitions happening in the Rocky Mountains mostly in spring and summer during the flood period. In the Northeast, they happen mostly in fall related to atmospheric rivers. And in the South, it's mostly in fall related to tropical cyclone activity. And this map suggests that these transitions are actually, again, driven by, no surprise any longer, different processes in different regions. And I'm here showing you the number of transitions independent of the season when these transitions are happening. The transitions that happen in summer, they are actually most frequent in catchments with a high snow influence. Here we again arranged catchments from no snow influence on the left and high snow influence on the right. And in summer, you see that those catchments with a high snow influence, they also experience the most transitions. This is very different in winter, where these high elevation catchments don't experience any transitions. Then it's more the catchments with some snow influence, between 10 to 30% of the total precipitation that falls as snow. And these are the catchments that experience or are most affected by transitions. And while we don't yet have any projections on how these transition frequencies are changing in future, we can still make some hypotheses on what climate change might do to these transitions. In summer, we're with climate change going from snow influenced to rainfall driven, and that might mean less summer transitions, which is a good thing. But then at the same time, we might see more winter transitions as we go from highly snow influenced to not snow influenced transitions. And we're currently looking into this in more detail with some detailed model simulations to then at some point be able to show you how indeed climate change influences transition frequency. Besides climate, humans also influence extremes through reservoir regulation. And this is just a picture from the Transe de Bagne, where the Manuela Reservoir was constructed in the 1950s. And you see that this reservoir has very, very strong influences, not just on the mean flow, but also on stream flow variability. And with impacts on variability, it also influences extremes. But first on reservoir influences, we've, for the Alps, shown that we can find two main regulation types. One type highlighted in green is the catchments where we do a lot of storage in the summer months during the snowmelt period, and a lot of release during the winter when energy prices are up and energy is being consumed. And then we have a second type of catchment displayed on the map in red, where we see not a very clear seasonal cycle in regulation, but the regulation is still there, and these are mostly the low elevation catchments. And the type of regulation is strongly tied to the stream flow regime, with the glacier-iced and snow-influenced catchments experiencing strong seasonal regulation cycles, and the more rainfall-driven catchments showing less regulation. Now, what does reservoir regulation do to floods and droughts? To answer this question, we've put together a large ensemble of catchments where we do have a natural upstream gauge, which is separated from a regulated gauge by some reservoir. And we simply compare stream flow statistic upstream of the reservoir to the stream flow statistics downstream of the reservoir for these 120 catchments in the US. What we find is that reservoirs tend to decrease flood peaks and flood volumes, which is great because that means we can actually use these reservoirs to potentially counteract some of the negative effects climate change might have on flooding. But this reduction in peaks and volumes happens a bit at the cost of extending duration, which is usually not a very big problem from a management perspective. Very similarly, we see that reservoirs also reduce drought deficits and minimum flows, which is also great news because these reservoirs can be used for drought alleviation as well as they can be used for flood alleviation. But of course, this overall picture is kind of counteracted by some of the reservoirs where you can also see the opposite effect and see that regulation actually leads to an increase in droughts and floods. Last, I want to quickly show you how reservoirs also influence the transition behavior. We see that going from natural to regulated catchments reduces the number of transition events, which is again related to the fact that there's less flood events, and the same happens in winter when we also see a reduction in these transitions. Now we've seen drought events have become more frequent, especially in summer. Flood events will likely increase in intensity and frequency, at least when we look at the very, very intense events. And we're also expecting to happen more frequent transitions. But at the same time, we do have some opportunities in terms of direct regulation to counteract some of these negative effects of climate change. We could, as society, further think about additional adaptation strategies, which can, of course, be, like engineering structures and reservoirs, but these could also be more nature-based solutions where we give more space to rivers and try to kind of enhance their capability of absorbing flood peaks in a natural way. And the same thing is essentially true on the drought side. Of course, you can build reservoirs that help you to alleviate droughts. But on the other hand, we could also think about how to use water more efficiently, how to reduce demand such that these kind of pretty stark changes in the landscape are actually not necessary. Overall, I've in this talk tried to show you that floods, droughts, and their transitions, they're influenced by both climate change and regulation. And in future work, I think we should also focus on the interplay between the two different effects and how we can use one effect to counteract the other. Then I think we should consider these impacts of climate and regulation on the hydrological cycle when designing hydraulic structures and when thinking about event management strategies. And we can use this information to develop suitable adaptation strategies. With this, I thank you for your attention, and I'm now happy to take a few questions before I hand over to Tom.
So thank you once more, Manuela. Now I will present briefly Tom Beucler before his presentation. Tom is an assistant professor in environmental data science at the Faculty of Geosciences and Environment of the University of Lausanne. His group operates at the nexus of atmospheric physics and machine learning. They aim to enhance weather and climate predictions while deepening our understanding of atmospheric dynamics. Tom is also a co-founder and member of the executive and scientific board of ECCE, the Expertise Center for Climate Extremes. Tom, the floor is yours.
Thank you, Charmely. Thank you all for your understanding, but also thank you for coming here today. I'm very grateful that we were lucky to host Manuela Brunner for our CLIMACT seminar this week. And I thought it would be an excellent excuse to discuss some of my earlier work on tropical precipitation and how it changes with climate. And this is part of two collaborations I was very lucky to be part of. And both of them are motivated by the fact that, and that was reiterated by the recent Intergovernmental Panel on Climate Change, we have high confidence that heavier precipitation events across the globe will increase in both intensity and frequency with global warming. And the reason we should care, I mean, I'm very lucky because Manuela already justified how important better understanding precipitation can be for water management, for floods and drought. So it's obviously important for climate change adaptation, and also more accurate estimate can help us with climate change mitigation. The other reason we should care about tropical precipitation in particular is that by 2050, demographic projections tell us that more than half of the world will be living in the tropics, and this is a particularly vulnerable population. Here I'm showing you an example of a heavy precipitation event in Bali. And what you can see is that these events tend to be much more intense. And I think you also saw it in the initial observational loop. And today I want to cover pretty simple questions about tropical precipitation changes. How much change are we expecting? Why are we expecting these changes? And where are we expecting these changes? So I'll start with how much. And I'm going to show you schematics I derived in a couple of seconds from the IPCC online atlas. So the reason I did it is that it's open and accessible. So I all encourage you to play with it. You can get regional projection for several variables. Here I'm showing you projection in mean precipitation following the SSP 8.5 scenario. So that was similar to the pink scenario that Manuela showed earlier. And what we can see if we look at global projection in mean precipitation, here it's a loop with 1.5, 2, 3, 4 degrees, is that you're seeing a lot of green. That's where mean precipitation is about to increase by 30, 40%. A lot of red, you can see that the storm track in the North Atlantic, for example, is moving, leading to less precipitation. But here you can see that that's almost as much red as there is green. So we only expect mean precipitation to increase by a couple of percent as the climate warms. And that's because the mean precipitation is constrained by the global energy budget. So it responds to the radiative forcing, and that's only going to be a couple of percent per Celsius warming. In contrast, if I look at extreme precipitation, so that's a maximum one-day precipitation in the year, you can see all of a sudden there's a lot more green. And so what that tells us is that in most of the world, there will be a significant increase in extreme precipitation. And it's easier to read if I stop the loop. So these are the other maps shown directly in the IPCC report on weather and climate extremes. What you can see is that the change is, there's a little bit of spatial variability, but it's mostly roughly 7% per Kelvin on average. And that's one of the things we'll cover today. And the reason for that is that unlike the mean precipitation, where we have mean energetic constraint, extreme precipitation are only limited by the amount of water vapor available in the atmosphere to condense and then rain out. And so I'm going to think a lot today about how we can interpret those extreme precipitation changes and introduce a thermodynamic versus a dynamic contribution. And that's been key to our understanding as a community of how extreme precipitations events change with climate. So the idea is that you can write precipitation extreme roughly as a product of a thermodynamic contribution. Here, I modeled it with the clouds and water vapor molecules. And so those are changes in how much water vapor there is in the atmosphere. Because most of atmospheric water is in the vapor form, and as soon as we condense it and it forms clouds, usually it rains out quite quickly. So that's one contribution, and then the other contribution is our ability to condense that water vapor into clouds, which is linked to updrafts. So as a storm forms, water vapor typically ascends. As water vapor ascends, it meets colder and colder air, and then that air condenses into clouds, and those clouds form precipitation. And so, as you may know, when we have the product, when a variable on the left is equal to the product of the two variables on the right, the relative changes can be summed. So the relative changes in percent of precipitation can be written as a sum of a thermodynamic contribution. And here you can see that it's all green and very uniform. So that one is the easiest one to understand for us. What happens is because of the Clausius-Clapeyron relationship, the warmer the climate, the more water vapor the air can hold. And so that's why we're seeing such a big increase in extreme precipitation, because we see extreme precipitation in places in the world where the air can hold the most water vapor. And we understand this quite well because the Clausius-Clapeyron equation is fundamental physics. And you can see here, roughly, you have all over the world 7% per Kelvin. Meanwhile, and that's where a lot of our uncertainty comes from when we do climate projections, the dynamical contribution is much more complex. So here you can see stripes where climate models don't agree. And you can see that in most of the world here on this map, they don't agree. And that's because it's really hard to resolve how regional circulations are going to change with climate. And so that's one of our biggest challenges for a lot of atmospheric variable, but in particular, extreme precipitation. So first, I'm going to present a study where we really asked why. Can we really understand these numbers in the most fundamental case to be able to, for instance, write theory about it and understand how it's going to change where our climate is going to be even warmer, or how it changed in past climate that were of different temperatures and characteristics. And for that, arguably the simplest model that gives us a realistic vertical profile of atmospheric quantities is called radiative convective equilibrium. And it's foundational because it's based on the simplest energy balance you can make for the Earth. So the Earth receives energy from the sun. Most of that energy is going to warm the surface, and then the Earth's surface is going to emit energy, both directly in the form of infrared radiation to space, but also in the form of temperature and water vapor fluxes that form storm. And so at the end of the day, if we look from for example, from space, if you take the entire atmosphere's viewpoint, there's a balance between the cooling you have from to space. So we emit this heat from the Earth's surface to space, and the heating we get from the sun, but also from these fluxes here that are indirectly forced by the sun. And really interestingly, these led to some of the first climate change projection. And I think you may have heard that the 2021 Nobel Prize in Physics was awarded to several climate scientists. That was a first for the Nobel Prize of Physics. And Manabe used radiative convective equilibrium to make some of the first projections of how the vertical temperature of the atmosphere was going to respond to climate change in the 60s. So this is not new. And these are quite realistic, and we don't deviate that much from them today when we look at the global projection of temperature profiles. And now you're wondering where the tropics come in, well, the nice aspect is that because in the tropics, the rotation of the Earth doesn't project too strongly, this is actually also a good model for how precipitation behaves in the tropic, especially on longer time scale. So that fundamental studies also allow us to answer interesting questions about the tropics. What I showed you may have been a bit boring, right? You're just seeing a vertical profile of temperature and you're seeing, okay, like, is that all we can do? Well, no, we have a lot of numerical simulation tools. So the nice thing is we can simulate this radiative convective equilibrium in a box. So you can think of that as storms in a box. And that's one of the simplest way we have to study the influence of climate change on precipitation, because then all we have to do is warm the box. So here I'm showing boxes that are colder on the top and warmer at the bottom. And if there was a movie, you could imagine cloud popping out. We call it popcorn convection. Clouds are going up and down. And clouds behave very differently in those different boxes. And then what we can do is in each box, we can look at the full distribution of precipitation and measure precipitation extremes. And then what we notice is that in that box, we can see precipitation being more and more extremes. And so that's nice because then we can use these very simple simulations to write theory about how precipitation is going to change with climate. So coming back to the separation of extreme precipitation I told you about. So now imagine we've been using very, very, very long boxes that look a little bit like the tropics. And we looked at how extreme precipitation, here it's the 99.9th quantile of the precipitation distribution. And we look at each temperature, how it increases. And what you can see here is that it follows these gray lines. And these gray lines roughly represent 7% per Kelvin, just like I told you before. So if we look at this plot to first order, roughly, it looks like 7% per Kelvin. But now we want to fully understand how it comes about. And we don't want to just understand it with some mean numbers. We want to really understand how the full vertical profile of vertical velocity, so the wind going up and condensing clouds, produces that number. And so what we can do is we can align the vertical velocity. So imagine a cloud is forming, you're looking at the velocity of the air going up. As the air going up, it collects water vapor. And as that water vapor is collected, it condenses and it rains out. And so here, what you can see is that you have to align the vertical velocity profile with what's to be collected. And I'm showing you what has to be collected on the left, so the amount of water vapor there is. For those of you who do thermodynamics, at the vertical gradient in saturation specific humidity. And what you can see is as climate warms, we go from blue to yellow. And what's happening is that as climate warms, the tropopause, which delineates the zone of the atmosphere we're living in, goes up and up and up and up. So then you're collecting water vapor higher, higher, and higher up in the atmosphere. So it would be misleading, and that's our contribution. A lot of the previous study would just assume this profile, the upwards air in the storm was always the same. But as you can see, because as climate changes, the troposphere shifts upward, it would be misleading to assume a single profile. And instead, you have to take into account the fact that it shifts. And without going too much into details, you can frame this as a conditional sampling problem. So that's the statistical part, but translated into simpler terms, because we're observing extreme precipitation, we know the atmosphere was really, really, really good at collecting the water vapor at the exact right height. And that tells us something about the coordinate change we can do to have a universal vertical velocity profile. And once we do that, we can write much simpler theory for extreme precipitation changes. And that was more the theory part, and it's published. So if you really want to understand the details of the theory, this is the reference to the paper we published in the Journal of Atmospheric Sciences. Now, you may be interested in more realistic situations, right? We do live in the Earth, and you may want to know what happens locally. For example, use projection. For example, what Manuela showed requires very precise projections at the regional scale. And the world is not so simple when you start to add continents, oceans, etc. So then what can we do? We now reach a stage of numerical modeling. We've made enough progress that we can run models that have a simulation, a resolution that is fine enough to resolve storms at the planetary scale. And we can run these models for several months in a row. And these are the kind of maps you get. So the previous movie was going to show you all the clouds moving around the Earth. It's really beautiful. You could look at these movies for hours. And now I'm showing you two models and the satellite observations. And a game I like to play is to ask the audience, okay, can you guess which one is the model? Can you guess which one is the satellite observations? Yes, it's in the middle. So yeah, the Himawari satellite is in the middle. And then it's the French and the German model on the left and the right. But we've reached progress in modeling that allow us to directly resolve storms. These models are extremely expensive, so they cannot yet be run for climate change projection, and they cannot be run enough to get reliable projections, many different ensembles for different scenarios. But what we can do is we can try to learn as much as we can from them. And that's where machine learning comes in, because thanks to progress in artificial intelligence, so here I'm using a deep learning algorithm. You can think of it as an algorithm that learns a task for itself without me telling it what to do. And it allows to, so when you look at these models, and now this GIF is working, so I'm happy. So these are the millions and millions and millions of vertical velocity profile you would get from looking at these models. So that's way too much information for simple statistical tools for the human brain to interpret. And so where machine learning comes in is you can train an algorithm on this millions of vertical profile. And here we train a variational autoencoder. And what's, I think, always very funny with these models is you train the model to predict the same profile, a profile from itself. Basically, all it's doing is it's taking the profile, it's compressing it here in a latent space, and then it's reconstructing that same profile. So you could say, okay, what's the point? Like you're just giving it a profile, it's giving you the same profile. How is that helping me analyze millions of profiles in an Earth, in a global storm resolving model? Well, where it really helps is that in compressing that data, it created a latent space, and it's a low dimensional space that's objectively created because I didn't give any instruction to the model, in which I can understand the dynamics at hand. So these millions of vertical velocity profile. And what I can do is that I can cluster this human interpretable space into regimes that can then be used to better understand extreme precipitation. So if we do that, we get 3 regimes. The first one we get is a marine shallow convection, so low clouds, and it also groups a regime with very little clouds. We have a deep convection regime, so that's the regime that produces the most rain in the tropic. It's these really big, usually cumulonimbus clouds. And then we have a third regime, which is the continental shallow cumulus. So this is low convection, but above land. And what's really nice is that I didn't tell the model anything. It analyzed this entire simulations, and I'll put the link so that you can look at it after the talk. These are really beautiful simulations, but they're impossible to summarize. And it did it objectively. And then what I can do is I can run, so some of these models can be run in a warmer climate, and then we can look at the changes in each regime. So then in each of these regimes, I can look in a warmer climate where they migrated. And when we do that, and we go back to our initial problem of extreme precipitation, what we find is that if we look at the change in extreme precipitations from much more realistic models, so these are the realistic tropics, we found that the thermodynamic change is still quite easy. We can say it's roughly 7% per Kelvin. You can make a few adjustments, but it's very easy. The really hard part, as usual, is the dynamical contribution. And here, using this technique, what we can see is that pretty much all of the complicated patterns is linked to how storms move around. So it's not so much that as our climate change, the way precipitation is going to be produced is going to be fundamentally different. So we may not have to dive really deep into how microphysical processes change. It's important, but for that particular projection, all we need to know is where the deep clouds went, where the shallow clouds went, where the places with no clouds went. And if we know that, that's enough to make reliable projection of how extreme precipitation shifts in space when climate changes. And so both of these papers are published, the one where we show how we can compare all these storm resolving model, and the other one where we can show how you can use this to confirm what we already know. We're not the first one to find that most of the spatial shifts are explained by storm type, and we find that very reassuring since we use more modern tools. We confirm what people already knew about where rain occurs in the tropics and where it's going to occur in a changed climate. So to summarize, how much? So if you come out of this talk with one number, it would be 7% per Kelvin. So that's the rate at which the atmosphere can hold more water vapor, and that's also the rate at which we see extreme precipitation increase with climate. And that's mostly linked to the thermodynamical contribution. And then the really hard part, and the part why a lot of us are still doing climate modeling, is that there's this dynamical shift, this regional shift in how circulation changes. And that affects many variables in the atmosphere, including precipitation changes. And I hope I convinced you it was an interesting problem, and we still have a lot to learn. But both observational progress, now this movie plays. So here it's remote sensing observation. So we now have combined satellite products that are excellent. This one is called iMerge. There are even better ones, but you can already see, and if you look at the colors, you can see that a lot of the extreme precipitation is happening in the tropics. You can also guess that that's a loop right before today, so we can see the little rain event that hit us today. And that's really where the frontier is, I think, being able, now we produce all these observational and model data, being able to analyze it and being able to rigorously assess how this is going to change with climate is really what we lucky and looking forward to research in the coming years. And if you want more details, here's the link to my lab resources, and thank you all.